Okay. So today, sorry, today we're talking about another type of algorithm called association algorithm. Okay. And the purpose of association algorithm is to understand if there is any association between one or more variables. Okay. So if you here we're talking, so it's not correlation. Okay. It is association. Okay. And association will tell us, okay, if two values are related. Now, if they are related, it means that, whatever action you take for one, you can take similar action for another, right? Now, this is used mostly for retail analysis, like for bundling. Okay, we say bundling in retail, for example, um, uh, you will hear this, right? Buy this and get this free, right? Or even in retail store, how they plan which product should be placed where. Okay, so in that kind of scenarios, association algorithm is used, and there are again a lot of other algorithms, but the main foundation, okay, or the main logic of every algorithm is a priori algorithm. Okay, so we'll talk about a priori algorithm, and other algorithms are like how to improve the time taken by a priori algorithm. Now, since these companies will have a lot of products, okay, and a lot of people visiting their store, it is actually challenging in terms of finding association between all the variables, because it's going to take a lot of time. And in fact, the data set that we're going to use, you can see that it takes a lot of time to find the association. But what is association? Okay, how do you calculate association? So if you see here, this sample bill that I have here, okay, so let's say these are six different bills, okay, and person one, okay, came and bought milk, sugar, and coffee. Okay, second person bought milk, sugar, and coffee. Third also bought milk, sugar, and coffee. Four, five, six bought just milk and sugar. Right? This is a sample six bills. Now you can see that everyone who's coming, okay, is buying milk and sugar. It means, okay, there's a strong association between milk and sugar. Right? People who buys milk, at least based on just six transactions, it means everybody who comes to buy milk also buys sugar. So there is 100% association between milk and sugar, right? So what decision can you make from here? Now, algorithm will just tell you that, okay, they're 100% associate. That's it, stops there. But what decision or what information can make from this? Of course, a lot of information we can decide. If you are in retail, probably you'll put milk and sugar together, or you will say, buy sugar, 5 kg sugar and get one milk packet free, right? Something like that you can make. So that is again um, the business decision that you'll make. But let's look at how uh, these are calculated, okay? How the association is calculated. So to calculate association, there are three important metric that you will have to understand. Okay, it's called support, confidence, and lift. Support, okay, talks about how important is one particular atom in your transaction, right? Now, you don't want to work with all the data, right? All the variables or all the products. So if you take a store, okay, it'll have maybe 30,000, right? Different SKUs, right? Or maybe even if you take, if you remove the variation, the product itself, there could be more than 5,000, 10,000. Now, it's very difficult to compare each product. Sometimes, two products together can influence one product. Okay, so it becomes very difficult to compare for all the products in the store, all the 5,000, 10,000 products that you have. So support is kind of filtering criteria. Okay, so we say, okay, let's look at the support of each of the product. And if support is more than certain value, only then we will include that data for our analysis. Okay. So support here you see refers to the default popularity of an item. How popular is that item in your store? Okay, or wherever you are talking about. So how do you know popularity? Number of transactions with item I is the formula here. Number of transactions with item I by total transactions. If your total transaction for that month, okay, you're taking is let's say 100, okay, and you see how many trans out of those 100 contains item I. So if item I is 1 or 2, probably it's not that popular. So you will say, okay, I'm not going to take, I'm going to exclude this product. Okay. Now if is like 30, 40, 20, 25, we'll say, okay, these looks, or you can even decide, okay, let me look at top 100 products, top 500 products, top 1000 products. How do you decide top 1000 products? By using support formula. Support formula is percentage of, okay, um, the product being sold. Okay, so you look at each individual. So here each row is your each bill, each transaction. Okay, each transaction, right? Okay, so that's support. Now, so support will help you to filter out products, right? One those which very less support you ignore so that you don't have to play with, you don't have to analyze all the data. Okay, the more data you have, more complex it becomes, more time is going to take, right? So you say, okay, I'm not interested in these products. So you leave them out. Okay. Now with whatever you have, okay, the next formula that we apply is called confidence. So confidence of product A to B. Okay. Okay. Now, when you talk about confidence, okay, product A to B is not same as B to A. Okay. Why? Because, okay, here it says confidence refers to the likelihood of buying item B, okay, if A is bought. So if A is bought, okay, then what is the likelihood of buying B? And reverse would be, that is A to B. B to A will be, if B is bought, what is the likelihood of buying A? Okay. So here we filter out all the transactions with, let's say, item A. So you'll say, okay, I'm not looking at all the hundreds. Okay. I look at only because I'm concerned about, or I want to know the likelihood of all the other products when A is bought. So you will take only bills where A is there. Let's say you have 25 such bills. So you'll take all A's, and then in that you will see how many times other values or other products are appearing. Okay. So here you see number of transaction with I1 and I2. With I1, we have filtered on I1. So denominator is I1. So if I want to know, okay, if I buy milk, okay, how many times sugar is bought? So I will filter out all the transaction with milk, and okay, that will be a denominator. Out of those transactions, how many of them have sugar also? So that will be your numerator. Now, vice versa may not be true. Okay, I mean, vice versa you'll do, but the value may not be same, right? So, confidence of this is milk to sugar. Okay, if I say confidence of milk to sugar, denominator will be milk and numerator will be subset of that conditional probability, subset of, okay, the denominator that you have chosen, and from there how many times, okay, sugar is appearing. Now reverse of this is confidence of sugar to milk. So denominator will be number of number of bills with sugar in it. Obviously that will be different than the first one. Within those transactions, within that transaction of the bills, how many of it has sugar? Okay, so it's not going to be same, right? Then third value that we calculate and which decides or which helps us to arrive at that association uh, value is called lift. Okay, lift is it says lift refers to the increase in the ratio of sale of B when A is sold. If A is sold, then how many times B is sold? Okay, so you divide confidence by support. Okay, you see, confidence of A to B divided by support of B. Okay, now based on the lift, okay, the one which has highest lift is what I mean, basically, end of the day, we are looking for lift. Okay, you want to know if I sell A, then what is the, then what is the ratio that B is also sold? Now, if the ratio is high, that means association is high. That means if you are making any decision for A, the B will also probably be impacted. Okay, so there is a famous example, okay, for this. So there's 7-Eleven stores in Japan, okay, and they have very small store. So what they do is they keep changing the products. So morning they'll have different set of products. Afternoon they'll change the entire product and they put new because they don't have a lot of space, like our big bazaar. They cannot have um, uh, that much products, So every time, based on the time of the day, because the customers that come in varies, right? So they would change the layout in the sense that what products is kept. Okay, and they were like, when they ran this, okay, they were able to find strong association between bread and beer, and they were like, how can beer be associated with bread, right? So upon further analysis, they figured out that, generally people would come in the morning to buy bread, okay? And since they're coming out to buy bread, they also bought beer with them. And they would put it in the fridge, okay? They would not consume beer in the morning, but they will buy, because they're coming out to buy bread. So along with bread, they bought beer and they put it in the fridge, and they would consume in the evening only. But it's like you are going out to shop anyways, right? Whatever you want to buy, you will buy. So when they saw that, they started putting more and more beer in the morning along with bread, and the sale of beer increased, right? Okay. So when you know that there is a strong association, then you can take various business decisions. And this is what this a priori or association algorithm will tell you. So in case of our example, okay, so if you want to find support for coffee, so out of total transactions, we have 6 transactions. How many of them have coffee? So it is 3 by 6, right? So your support for coffee is 0.5. Okay. Then what is confidence of coffee to milk? Coffee to milk. So coffee we're talking about. So denominator will become coffee. So how many bills have coffee? 3. And out of 3, how many have milk? 3. So it is 3 by 3, right? So it becomes your 1. So your confidence of coffee to milk is 1. Okay, now if you take reverse, you take confidence of milk to coffee. So milk, how many transactions are there? All 6 have milk, right? So denominator becomes 6. And how many of them have coffee? 3. So you see, the confidence of milk to coffee is 0.5, right? Confidence of coffee to milk is 1, but milk to coffee is 0.5. Okay. So now if we talk about lift is lift coffee to milk is confidence atom coffee to milk, which is 1 divided by your support for coffee or milk. See, I2 is there, so I2 is down. Whatever is on the right side, that is what we are taking. Okay. Right? So, did I get it right here? So, lift of coffee to milk is 1 divided by support for coffee to milk. So, support for milk. Milk is again how did I get this? Confidence of coffee to milk is 3/6, is it? Okay, so I might have got it wrong here, but that's okay. Okay, let's move. So when you see that lift is more than one, that means there is a strong correlation. Okay, so we look at lift value which is more than one. Okay, so here, okay, we are going to use our a priori algorithm. Okay, now a priori algorithm is not part of your sklearn. Okay, of course, we are going to use a priori, which is another library itself. Okay, which will help us to run this. Now, and when you're running this algorithm, okay, we define our minimum, um, your confidence, minimum lift. Okay, you'll say that I'm interested in, okay, with minimum confidence, right? And confidence is important because higher the confidence, okay, your less products will be put it for the analysis, which means your efficiency will be faster, right? But which also means that you may not be able to see the association of all the products, right? So some products may have low um, uh, confidence, but might be strongly associated. But you know, uh, but that's okay. Okay, they may be strongly associated, but if the product is not popular, okay, you don't want to spend time on finding its association also. It's like this, right? If product is sold more, that's when it makes sense to do something, right? If product is sold less, and if you come up with those bundling or any of these ideas, it's not anyway going to help your business. So again, you have to run the algorithms multiple times with different values to see if you're getting a right output or not, right? And once you get this lift, then okay, you can decide what strategy to adopt for your store. Okay, so again, it's a simple algorithm. Okay, and let's go back to our pie chart. Meanwhile, let me check the bill that we have here. So GitHub. Shopping list that you see, okay, is that the one? I don't think, is that the one? Okay, so this is different shopping list. Okay, you have date, and you have each separately. I'm going to use different one. Okay, market basket optimization. Okay, you see here. Okay, now you see this is the bill. This is, so there's no column here. Okay, your first row talks about person one. So this fellow has bought shrimp, almonds, avocado, vegetable mix, green grapes, etc. Okay. Third, um, transaction is only one item, chutney, right? So this is the bill. Okay. Now let me click on the raw version of it. Let's see if it is working today. Meanwhile, I'll go to PyCharm. PyCharm is ready. So I'm going to say link equal to the data, small data sets, and I'm going to copy this file name from here at least. Okay, I don't think it's working. Okay, so now data set equal to pd dot, what is pd? Import pandas as PD, right? So PD dot read CSV, okay? And here I'm going to give the link. Done. Okay. Now, okay, so I mean, if you want to see, you can print df, okay, and we will run it. Meanwhile, let's start building our algorithm. So um, I'm going to use, now you see this? This is the build. So it has 7,500 rows and maximum 20 columns. And not all columns will have values, right? That means when you say 20 columns, that means the maximum bill has 20, the one has maximum number of items has about 20 items. But you have seen that there are some one item also in the bill, right? Not everybody will buy same amount of products. Okay. So we'll see how do we to handle it. So import APY ORI. Okay. And this one has, so I'm going to import. So we'll say from Apriori. Okay. Import APRI. Apriori. This is the algorithm we are going to use. But before we use, we have to make this transaction a list. Okay. So I'm going to go through each of the product for I in the range. Okay. And I'm going to say len of df. So len of df will give me number of rows. So I'm going through each row and creating a transaction. So I'm going to create, sorry, transactions equal to list. And here I'm going to say transactions dot append. Okay. And okay. Now here we will run the for loop on the entire row and get the values. So how do you run a for loop, single value for loop? So I'm going to say for j in, okay, range. Okay, now you see maximum column is 20, right? So I'm going to put this as 20. Or you can even say shape of 1, right? Shape of 0 is rows, now shape of 1 is columns. You can use that. So for j in range 20, I'm running for j in range 20. Okay, and the result of this, okay, I want to store. So how do I get the store? So it is df dot values. Okay, values, which values? So I, okay, so row is first fixed and j is your column, right? Which will keep on moving for each of the rows here. So df dot values, okay, and so this has to be converted to string. So I'm going to put str of this. Okay, so this is loop is going to return as the values here. Okay, which I'm going to append here. Now this entire thing, okay, should be returned as a list. So I'll put a square bracket here. So this entire thing becomes a list. Okay. Now, if we have got it right or not, we are going to check. I'm going to say print transactions. Okay, let's run it and see if all the values have been converted into your list or not. This is the data frame. Okay, now data is ready. Okay, if this works, okay, if you have no error here, that means this is ready to be given as input to the machine learning algorithm, which is our a priori in this case. It does take time because it has to iterate through all the 7,000 rows and form the list, but it shouldn't take so much of time. A priori algorithms are time consuming. That's why you'll talk about Eclat, FP growth, and other algorithms in association. This is the core, okay? On top of this, on top of a priori, these algorithms are based to make them run faster. Okay, so FP growth has its own logic, Eclat has its own logic, but at the core, it is same algorithm. There's only one algorithm which does the association. Okay, let it run. Okay. Um, only doubt, my doubt is if I've got it right. Okay, it looks like it's correct. Okay. Meanwhile, let's build that um, um, what do you call that algorithm? Okay, so we'll create the object. So I'm going to say association algo equal to your a priori. Okay, and here we will pass transaction. It takes transaction as input. Okay, your list, and then along with the list, it needs okay minimum support, minimum confidence, minimum lift. You can define all these three values. Okay, minimum confidence you can say, let's say 0.3 maybe. That means I'm saying 30%. Okay, 30% is actually too big. It's in reality it's very difficult to find any product with 30%, right? So we'll put 0.2. Let's see if it works or not. Then you can have minimum uh, support. Oh, support I meant. Okay, 0.2. So you have support, you have confidence. Okay, and let's say we put minimum lift. Now, lift, we want these values to be more than, okay, we want this as to be more than um 1, right? So let's say here I'm looking only for those more than 2. Now, still I feel support is too high, 20%. We may not see any values more than 20%. So 2% we'll put and see what happens. Why does it get stuck? Not stuck, is it? Let me. So did I get it right here? Transaction.append. Now for J in range 20. So J is going to be 20. Now, instead, what I'll do is, okay, let me do one. If I mod 100, okay, so I'm printing every 100th step. Let me see if it prints or not. I0, okay, I100, yeah, you see, so much time it's taking, right? And we have 7,500. Yeah. And okay, so let's continue to build our algorithm here. Now, this will give you the association values, okay? Now, if you want to print it, you can say print association equal to um, and here it's actually list of your association algo. That is it, okay? If you run it, you will get this. Now, what I'll do is, okay, I will stop this here, okay, and I will run it again, okay. Meanwhile, let it take its time. Meanwhile, we'll go to our notes again. And we'll talk about the other um, algorithm that we have, right? So this is what we just did, okay. Now there's something called as Eclat. Okay, Eclat stands for equivalence class transformation. So it's an improved version. I said right. Core logic is this one only. Okay, find support, find confidence, and then find lift. Okay, and check for values which are more than one. Higher the association, okay, higher will be the lift value, right? So you can check that. Okay, now coming to this example here, Eclat, same example, okay, same thing, okay. But what we do here is Eclat algorithm starts with minimum support. So we say threshold, okay. So, and you also give number of transactions that you want, okay. Now here, okay, you see, you're calculating support for all the products. So milk, sugar, coffee, and then all the combination, right? It is possible that milk, sugar together can influence coffee. So it's not always 1 to 1, okay. It can be 1 to 2, which is probably rare, but 2 to 1 means if those who are buying milk and sugar also buys coffee, right? If they're buying milk and bread, they also buy tea. That is also possible. So all the possible support value, all the possible calculations are done. So Eclat, okay, spends time before running the model, calculate support for all the values, and then you add one more parameter here called as threshold. What it means that if threshold is your support, and if I give here, let's say threshold as 4, for example, then you see only these four values will be compared. Okay, even coffee will be dropped, right? So milk, sugar, and milk and sugar is only taken into account. All these other values which are less than 4 support will be ignored. Okay, so this is looking at the number of product itself. Okay, in the appearance. Now, Apriori doesn't distinguish between this, but Eclat actually does this. You filter out, and then you continue to build. Okay, so then you run Apriori again. So this is just an extra step over Apriori. So we're saying that okay, we'll look at this complete support of all the values, and we will filter out, okay, based on our criteria. Okay, so Eclat, of course, you can check this. Then you have one more algorithm called as FB growth. Okay, now FB growth is called as frequency pattern growth. Okay, this is another improved version of Apriori, right? And here we create ordered frequent items to see which are the frequent items, and one which are more frequent is taken as input to the algorithm. So here again, just like Eclat, you have to find first support. So okay, you find the frequency first, right? So here you see M for milk, sugar, coffee, tea, and bread. Let's say this is my bill item. Okay, so I have milk, sugar, coffee, tea, and bread. Now, if you see here, milk, tea, and coffee here. Now, what is the frequency of milk? Milk is in all the 6 items. So M is 6, S is 5, right? Except one, everything has sugar. Then coffee, tea, and bread. Now, I say threshold is 2. When I say threshold is 2, bread is removed. This is your Eclat algorithm, right? You remove it. Now, what it does is, okay, we create what is called as ordered frequent item. Now, this is all done by the algorithm. We don't have to do it. I'm just showing you how, what is the extra step performed by FB growth. Okay, so we create ordered frequent items. Okay, now these are the items. Okay, and we created these frequent items based on your minimum threshold, right? Since we said 1, right? We removed bread, right? So your bread is not there. But if you see, everything is same. Now, MSC is MSC. MTC became MCT. Why did it become MCT? We looked at the frequency of each item. Okay, we looked at the frequency of each item. Now, though it is in the bill, you have tea before coffee, but coffee has more uh, frequency, right? So that's why. So milk is 6. So milk always be first, right? Then would be your second item. Okay, second most repetition is by coffee. Okay, in MCT. So your C comes next, then comes T. Same way, you have MST, MS, 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 right? So one, you will order in high to low frequency order, appearance order, and then remove those items which are below the threshold value, right? So we have removed bread here. Okay. So this is step number 2. After calculating threshold, step number 2 is this. Now we have to build a tree data structure. Okay. Tree data structure, you have root, and you take each transaction and you start building this tree. So transaction 1 is MSC, right? So and then you have MCT. So MSC, you build a path like this. MSC, you build. Then, okay, when you're taking second transaction says MST. No, it is MCT, right? MCT. So from root you start, you come to M. Second time you're visiting, right? First time you visited M1, S1, C1. Second time you're visiting M. So the reference count of M becomes 2. Now after M you have C. Now if you follow this path, you cannot come to C without going through S, right? You cannot go to C without going through S. So you said, okay, since I cannot go to C directly, I'll create a new path. So you create a new path here and you have C and you have T. So in this case, C is 1. Okay. Now let's see, let me build this, okay? Then probably it will be easy. So meanwhile, see our algorithm, where does it go? So it is still 6,100, guys, okay? 6,200. Okay, so I'm going to take this one and go to paint here. Okay, and I'm going to paste this here. Instead, let me make it small, okay? Let me go here, take a smaller. Okay, we have already understood how to draw this one, right? So I'm going to take this. I don't have to do it from scratch. And we will take other transaction and try to complete this tree. Okay, so this is what we have done, or maybe we'll delete it and we'll draw a little bigger. So you have root, right? Now from root, it is MSC. So, you know, you take this, okay, you go and you say right? M is first 1, so I'll put 1 dot here. Then it is S. So after, so you have S here. And you'll put 1 more S dot. Then you have C. Okay, so you have C. Okay, then is MCT. So you have to come from here. This is your root, right? So you have to come over here. So M becomes 2. You cannot go to S. So you will have 1 and it will be at the same level, okay? You have to have at the same level so that later when we are doing counting, it becomes easy. And then you have T. Next one is MST. Okay, MST. So now again you come here M, then S you'll go straight, and now you have T. So what we'll do, you will come here at this level and draw T. So T will be at T level only. Okay, so you get T as 1. Correct? Now you see. Okay, so MST is done. MS, 3 times MS. So you come here, you have M and you have S. Then again you have M and you have S. Again you have M and you have S. Okay, so we have covered all the 6 transactions. Now, see, these are done before we run the same logic that we are running right now. Okay, so this is your final tree structure. Now we create what is called as conditional pattern. Okay, so I'll say conditional pattern. Now, what is your conditional pattern? In conditional pattern, we take these products. Okay, so you have generally we take from low to high. Okay, you take tea, coffee, then sugar, then milk. Okay, now you see how many coffee, how many sugar, how many milk you have. So tea, so when you take tea, you have one ms, right? And one mc. Only one mc, right? So one ms and one mc. So you will create here as m comma s, which is 1, and m comma like c, okay, which is also 1. Okay, then if you take c, okay, c is here and here. For c also 1, right? So c, you have ms1 and m1, right? So here you have ms1 and ms1. Next comes your s. Now if you take s, right, how many times you have m with s? Look at the value here. 3 plus 2, 5 times. So ms, okay, ms is 5. Okay, m is anyway starting, so it is, we don't ignore. So we don't have to check m with m, milk with milk. Okay, so you come up with this. Again, you can have a criteria. You can say that I'm interested in value more than 2 or 3. Okay, now when you go through all this, look at the common element here. What is common? All of them have m here. Here you have m 2 times, here you have m 2 times, here you have m 5 times. So it says that you better check with m, and then what is the second highest? S, right? So you can define the minimum value here. I'm not interested in 1. So if you're not interested in 1, okay, all these will go away. So now you have only m and s to look for, right? So when you have only one and m, of course your algorithm will run faster. You don't have to go through all the 20 columns like a priori. We only have to go through 2 values here. Okay, so this is the logic of FB growth. Okay, and they form this conditional pattern, okay, using tree method before the same a priori algorithm is run. So here, see, the purpose of Eclat and FB growth is to give minimum values to a priori. Okay, so that your a priori performs faster and better. Otherwise, a priori is slow. It is very slow. Okay, just with 7,000 rows, our program is still running. Where is my pie charm here? Here. Okay, you see, we got this association. So it says beef with spaghetti is highest. Then you have, okay, the second one is spaghetti. Okay, so it's still talking about the first one. So, okay, so association, okay, you see, this is your list item. Okay, so the relation record is this. This is ordered statistics. Let's look for next relations record. Okay, then you see relation record here. Spaghetti and olive oil, right? Spaghetti and olive oil is second item. Okay, it talks about other things. It talks about the support, talks about the confidence. Okay, now, so we should have removed NaN. Okay, it has taken NaN also as one of the data. We should have removed NaN from here, from the list. Okay, from the list, you would have said, okay, just remove all the NaN values. So we should have After creating transaction, remove nan from the list. Make sense? So this is how you run, algorithm, and this is what you get output of a priori. Eclat and FB growth you can run on top of a priori to make it work even faster. So this is how you can run association algorithm a priori and find association between different values. All right. We'll stop here for today. Any questions, please let me know.